This video will show you how to recreate the plots in section 4.2, the reversible linear reaction, in Mathematica using a manipulate object. So to begin with, we want to create the reaction x1 goes to x2 reversibly. To do that, we say reactions equals, using the function string to mass, you put in a string. First is the name of the reaction, we're going to call it v1. Then the inputs, the type of reaction. This is for a reversible reaction. This is for an irreversible reaction. And then x2 is the output. And you get it in toolbox form. x1 goes to x2 reversibly. Then we want to construct the model. And we just put in the reactions. And we want to also designate the initial conditions. You can press tab if you want to autocomplete ever. And according to the legend here, the caption here, x1 at 0 is 1, x2 of 0 is 0. So we say m of x1, which is a way of turning a string into a metabolite. M is short for metabolite, and see now we have x1 in the terms of a metabolite. And we can show that in full form. This shows the full form of what is actually displayed. So m1 goes to 1 for the initial condition, mx2 goes to 0. Then we also have the parameters, which are the rate constants. We're going to define these up here. k1 is 1, and k negative 1 is 2. Now here, inside here, we're going to put the option parameters, and that goes to a list k of v1. So k of v1, if you do the full form, is actually the rate constant v1 true. If you want to have the reverse reaction, you do k v1 false, and that goes the opposite way. But if you don't specify anything, then it assumes that it's a forward reaction. So the forward reaction rate is 1, as you can see down here, and then the reverse reaction rate, we already defined those as k1, and the reverse reaction rate is k of v1, comma, false, and that is k negative 1. The reason why I defined these already is because we're going to be using those later on when we're defining the pools, and also when we create the manipulate object. These are the two variables that we're going to want to manipulate. So I just defined them here so we don't have to go back and change them later on. So if you run this, you get the model. Now you want to simulate it. So you say the concentration, so the simulation creates two lists, the concentration list and the flux list. And you run simulate model, let's say from 0 to 100. So here's the concentrations, and here are the fluxes. Now we can start making the plots. So the first plot is a phase portrait of x1 versus x2. So we're going to say plot phase portrait. We can just type in conc because this right here is just x1, x2 and their rules. So if we plot it, it's going to come out really weirdly because the range of the plot is very zoomed in. So we want to change the plot range by using the plot range option and start with the x values going from 0 to 1, then the y values from 0 to 1. So now it looks a lot closer to this. It's missing a few things. So first we want the axes labels. So we use the axes label option, and we want x1, x2. So that gives the x1 on the x-axis and the x2 on the y-axis. And then we'll do plot label for the title, and we're going to call this A, phase portrait. Okay, so the first plot looks good. Now we're going to go on to the second plot, which is the concentration profile of x1 and x2. For this, we say plot simulation, the concentrations, and we want to go from t from 0 to time goes to 2. Now plot simulation automatically starts by making a log-log plot. We only want a regular plot with linear axes. So we say plot function goes to plot. And now this looks much closer. You can also mouse over it to see which metabolites they are. Now say that you want to make this a little clearer, we can make a legend by doing plot legends option goes to, and then you put the first one, second one. And now we have a legend as well. We also want to put in the axes label, but we only need an x-axis here. So I'm going to say plot or axes label. And to just do the x-axis, you put in a list and you say time. And now we have the x label. And if we want the plot title, we say plot label, and then we do the string b time profile. So that looks pretty good. Now the final plot is the plot of the pools. So first we need to define the pools, which are x1 minus x2 over k1, and p2 equals x1 plus x2. So p1 equals m x1. Remember that all of these are in the Mass Toolbox format, so you have to put it in as a metabolite every single time. Divided by, and this is where defining k1 and k-1 comes in very handy now. So that's k1 over k-1 is the equilibrium constant. So that's pool 1. And we need to slash dot this, which means replace all with the concentrations. And then we want to define pool 2 as m x1 plus m x2. And once again, replace all the concentrations. So that way it doesn't just stay as metabolite, it goes back and replaces everywhere that it has metabolite x1 with this interpolating function. So now that we've defined the pools, we can plot them just by using the plot function, pool 1, pool 2. And we want to go from t goes from 0 to 2 also. So this looks pretty close. Now let's put in the legend again. So plot legends goes to pool 1, pool 2. And then we want to put in the axis labels, which once again will just be time on the x-axis, and you also want the plot title, plot label, which is C time profiles of pools. Alright, so now we have static images of these plots. To make it dynamic, we have to use the manipulate function. To learn more about the manipulate function, or any function, you can do !manipulate, and that gives you a couple of different ways that you can call the function. And if you click this, it opens up the documentation, which has a lot of very useful examples all about all the different options, and you can learn more about how to use any of these functions, plot, manipulate, you name it. So for the manipulate function, we want to just put in all of these different equations, or expressions. So make sure you put a semicolon after each line, or else it'll think that you're multiplying out different expressions. It's a common source of bugs. So always semicolon after each line. So model, you want to put in the simulation. Then you want to put in the face portrait. And for the images, we're going to put them in a row. So row takes a list as the input, and whatever's in that list are the things that are going to be in the row. So the face portrait is the first one. Here we're going to do commas because we're now dealing with things in a list. The face portrait, the simulation, and then the time profile of the pools. So commas inside the list, semicolons outside of the list. Oh, and we also need to define the pools in here. So now, the last thing we want to do, so this row, we actually want it to show, so we don't put a semicolon there. Instead, we're going to put a comma, and here is where we define the items that we are going to manipulate. So like I mentioned all the way at the beginning, we're going to change k1, and we're going to let it go from 1 to 5. And k2, we're going to make it go from 2 to 5, k negative 1 goes from 2 to 5. So as you can see, when you type in k1 and k negative 1, they turn to a different color. And that shows that it's inside the scope of this manipulate. So this k1 here is actually different than the k1 out here, which is defined as 1, but in here it can change to different values based off this manipulate function. So now if I run this, we have our pictures, our plots, and they're very small and very hard to read. So let's add an option to each of these. Image size. So it gives us a couple options. We can do tiny, small, medium, large, full. I personally prefer to give it the pixel width. So we're going to say image size goes to 300. And if you want to know about different options, you can also do question mark image size, and you'll get a documentation page on that option itself. So now that's much better. You can see the image is much easier. So I'll expand this a little bit. And now when we change this, you can see how the face portrait and the profiles change. So a weird thing that happens is if you increase k1, you notice that here the axis changes. So to fix that, let's invoke the plot range option again. And we want this plot range to go on the x-axis from 0 to 2, and on the y-axis from 0 to 1. That way, no matter what our k1 is, it'll always have the same plot range. And you can also click this little plus button to see what the actual value of these variables are. Now say that we want to see what happens when we bring k negative 1 all the way down to 1. We can do that, but unfortunately it starts at 1. So if we want k negative 1 to start at a different value, we say k negative 1, comma 2, and that gives it the default value. And see, now it starts at 2. And we can bring it down to 1. Another thing we can do is put in the name displayed over here in the manipulate object. So I'm going to call subscript, which takes in two inputs, so k and negative 1. And I'm going to do the same thing over here. So we need to put this into a list, say the default value, which is 1, which is the same as the normal default, but this always has to be the third input in the list. So now we run it again, and we have these fancy little subscripts here, so k1 and k-1. And that shows you how to manipulate objects for the first graph here. So the last thing that I want to do is show how to put all of these variables into a module. That way, when we call them outside, they won't already be defined and it won't mess with anything else that you're running in your kernel. So if you type in module list and close it off here, then you can define different variables and these variables will not be able to be accessed outside of this. And they also will have different definitions than the variables that we already defined out here. So say that we rename this, let's call this actually reactions. And then here, we'll call this reactions. So when we run this, it runs perfectly fine. But if we call reactions outside, it doesn't know what that is. So that way, if you call some variables in here and you want to do a couple of these manipulate objects, you can just put them all inside this module, and that way you know that you're not messing with any other code. And you can see that all of these variables are green, which means that they're inside the scope of the module. And that is how you convert the reversible linear reaction from section 4.2 into Mathematica into a manipulate object.